How do you know if something precipitates based on your Q and your KSP? So, in this case, we have three different kinds of solutions. We have saturated, unsaturated, and supersaturated. So, let's just take a look at the initial saturated. So in this case, saturated, we're going to think that it's not unsaturated, it's not super, so it's probably somewhere in the middle. So in this case, the answer is going to be the maximum amount of solute that can dissolve in a solution. So your solution is the amount that aligns perfectly with that. In this case, that means that our Q is going to be equal to our KSP because we know that our KSP is at equilibrium and Q is that value that we have when it's not, but in this case it is. So unsaturated, then let's look at our options. I'm going to say un is probably less. So unsaturated solution contains less solute than the solution is capable of dissolving. So you think about in solution, we added enough to our solute so that if we add however much, it's going to dissolve, and there's even more ability for that solution to dissolve whatever the solute is. In this case, our Q is going to be less than our KSP because our products over reactants, we know that that's smaller, so we could have more products. Lastly, we have our supersaturated, so whatever we have left, our Q is greater than our KSP, and this definition makes sense because a supersaturated solution dissolves more solute than the solution is capable of dissolving, which means that you have a leftover in the form of your precipitate. So let's do a math problem to explain how this all works. So looking at this math, so we have a KSP of a PbCrO4. So my first step, I'm going to make sure that I just break that down into its components. So in this case, it's going to be equilibrium arrows, but I have Pb2 plus as aqueous, and our CrO4 2 minus also as aqueous. Now our KSP is equal to Pb2 plus our CrO4 2 minus. Our coefficients are 1, and we know that in our K equation, our PbCrO4 as a solid is not going to be included because we don't include solids. So then finding out how much we have of each separately. So my first step is going to be looking at my CrO4 minus. So to find my moles, I know that moles equals my molarity times liter because that's going to cancel out our bottom as if it would be equal to moles per liter times liters, where I'm canceling those. So my moles of my CrO4 2 minus are going to be equal to 0.0020 molarity times, I'm going to just have my 25 milliliters as liters, so I have 0.025 liters. We see that I got that from this molarity and this volume. So I know that I'm going to have 5.00 times 10 to the negative 5 moles of my CrO4 2 minus. Then if I go over and I do my Pb2 plus, it's the same exact math here, just on the other side. So my moles, Pb2 plus, I know that I have my 0.000125 molarity times my 0.075 liters. I got that from this molarity and this volume. So I know that I'm going to have 9.38 times 10 to the negative 6 moles. But then we're going to take these values and we're going to divide by our new volumes. So if we think about it, this whole scenario is just an M1V1 equals M2V2. So we found our amount of moles. Now we're going to use our V2s to find our final molarity. So we added 0.075 liters of our PbNO32. We added 0.025 liters of our KrCrO4, or K2CrO4. When we divide by both of these, we get a new value over here of 9.38 times 10 to the negative fifth, and we get 5.00 times 10 to the negative fourth molarity. So in this case, we see that whatever we have left over when we multiply this, our Q is going to be greater than our KSP, so that leftover will form a precipitate. Supersaturated solution.